Welcome, everyone. This is Gabriele from Open Systems Lab, and this is the first of a series of videos that we would like to provide for people interested in designing WikiHouse. And this is a video specifically for structural engineers and for structural engineers that might come across WikiHouse for the first time. And we would like to provide some tools to facilitate the design of WikiHouse. And specifically today, we're going to talk about how to design WikiHouse for lateral loads. And we're going to focus on shear walls. There's a series of resources which I am going to link at the bottom of this video. This include some of the experimental testing that we did and include also some of the analytical modeling that we did in the past and some of the equations that we used to match the failure modes that we observed in the experimental test. So hope you enjoyed it. Hope it is useful to you, and it might make your design process hopefully easier. Right, so let's jump into Rhino and have a look at the at some of the WikiHouse's block. So here you see some of the WikiHouse columns that support the WikiHouse beams, which are connected to the end blocks, which are connected to the foundations. And the way the structural system works is the fact that columns are connected to each other by using these elements that we call bow ties, which are essential elements that work in shear and also in tension. So there's sort of shear keys, but also hold down when they're placed, especially between the column and the end beams. And this is a typical configuration of the wall, and we're going to see how this wall can be actually calculated in the next part of the video. So generally speaking, what we want to do as structural engineers is checking that the demand, the loads bearing on our structures are lower than the capacity of the structure itself. And the terms capacity means both strength, but also stiffness, right? So we normally want that our structure to be strong enough so it doesn't break under exceptional loading conditions, but we also want our structure, and we also want our structure to be stiff enough so it doesn't deflect too much under normal loading conditions. Now, about calculating the demand, I think this is well understood and it's common practice among structural engineers, depending on the site location and the building code that you're using. If you're in Europe or if you're in the UK or in the US, there's a specific building code to calculate the demand. But what I would like to explore in this video is about calculating the capacity of WikiHouse, because that is probably something that is specific to WikiHouse in terms of the structural system and the materials used. So first of all, let's have a look at what is the structural system resisting lateral loads in WikiHouse. And the system that we do use to resist lateral loads is shear walls. So essentially, when we join our columns together by using bow ties, they form a shear wall. And we take advantage of the shear wall to take any horizontal load acting on our structure. So this is probably the typical scenario that we have when we want to calculate a shear wall. We have a specific wall with a certain height h and a certain width, and the wall is subjected to a vertical load, which is probably coming from our roof or our floor, and is subjected to an horizontal load F. In case your wall is at the first floor and you're considering a two-story or more than one-story structure, you will also have an overturning moment on your wall, and that overturning moment is coming from the shear that you have at the wall above. So if you have a single-story structure, you probably just have a lateral load force, most likely. If you're working with a two-story structure, the wall that you have, for example, at the base floor, will also be subjected to overturning moment M, which we want to provide information about that as well, so we can cover the most general case. So there's the question is, how is our wall going to behave, our WikiHouse going to behave when we have this sort of loading scenario? So there's a good paper, which I'm going to link in the description, which provides some analytical models about how to calculate cross-laminated timber walls, which are the standard solution for shear walls. And I decided to adapt most of that paper, most of those equations into the WikiHouse wall, because I think there's a very good parallelism between the two systems. So if we are thinking about pushing our wall, there will be essentially three deformations, three mechanisms that occur altogether to calculate, that contributes in deforming our wall. So the first mechanism that happens is a translation. So if we imagine our wall to be a rigid block, there's a translation at the base of the wall, which is due to the fact that our bow ties, which are the connectors between our wall and for example, the foundation, the beams, our bow ties are deformable objects, so we can think them as sort of springs. They have their own shear stiffness, and the fact that they have their own shear stiffness means they can displace. So there's a deformation which is due to there's a deformation in the wall, which is due to the deformation of the bow ties at the bottom. The second mechanism is a shear, and it's due to the fact that we have some shear panels, shear facades on both sides of the wall, which made the cassettes, which are subjected to shear as well. So we have a deformed shape like this, and you will see later there's actually a very nice formula, which is pretty well standard formula for calculating the shear deformation of rectangular walls. And then the third component, which is the dominant one actually, is rocking. So if you think about what is happening in your wall is trying to rock over a sort of a pivoting point that is around the side of the wall. So there's a little bit of there are different studies in research on what that pivoting point is in cross-laminated timber walls. There's not much different in assuming the point to be exactly at the far side of the wall, or assuming that point to be a little bit on the inside. As from the capacity and rotation perspective of the wall, it doesn't matter too much, at least according to the literature review that I carried out. But I will link you the paper into the video. You can see by yourself what is actually the effect of these assumptions. But for our WikiHouse wall, for sake of simplicity, we will assume that the rocking point is going to be the on the farther side of the wall. So the question is, what is preventing our wall to translate, to shear, and above all, to rock? Well, the elements essentially that are doing the hardest job in preventing all this mechanism are the bow ties. And these bow ties will act in shear and tension in order to prevent the wall to displace, and in order to prevent the wall to fail. They're going to hold down your structure. So I will share you in the next part of the video how we can, first of all, calculate the bow ties, which might seem trivial, but it might not be. And in the second part of the video, we will see how, once we know the properties of the bow ties and how we can calculate the bow ties, how we can calculate the capacity of the wall based on that. Right. So the place I would like to start to talk about the performance of WikiHouse walls is starting with the bow ties. So as we talked through in the previous part of the video, we did recognize that the bow ties are the elements connecting the columns together. So they act as shear keys, and you also connect the columns to the end beam or the normal beams. So they act as hold downs. And what I'm showing here is part of the document that you can find linked in the description of this video, but it takes you through some of the observations that we made when we were testing the bow ties in tension. And that is really interesting because you can see the different failure modes that we observed while the actual elements were tested, and is interesting to see how this then can be predicted. So if you go through this PDF, you can see the details, but essentially there are two possible ways that we observe the bow ties failing. One is a tensile failure in the middle of the bow tie, and the other one is a sort of compressive shear failure at the essentially at the intersection between at the contact surface between the bow ties and the surrounding panels. So let's jump now into the spreadsheet, and let's see how this failure modes can be predicted by using analytical calculations. So here we are in the spreadsheet. This is available for everyone to use, so hopefully it will provide some further help in calculating the shear walls. So this spreadsheet is made of 4 sheets, and at this stage we're going to look at the bow ties. So we're going to use the bow tie calculator section and the material database. So in this initial part of the Excel, what we're doing is essentially setting out the geometry properties of the bow ties. So during the testing that we did on WikiHouse specimens, our bow ties changed dimensions a few times, and we were trying to find the best combination. And this image you see here is the final version. So this is what is used in version 0.2 at the time of recording. So all the geometrical properties are listed here. You will see this other bow ties with different shapes, that some other bow ties that we tested. The analytical model is still valid. Yeah, don't get confused, please, if you see different shapes. But essentially, at the initial part, in the initial part of the Excel, what we are doing is setting the geometrical properties of the element, and then we have 2 entries here for specifying the stiffness of the bow tie in tension and the stiffness of the bow tie and shear. Now you can find these values in the PDF file. I'm going to link it to the description of this video, where you can find the whole experimental testing of bow ties and how these values were found. But essentially, this is something we measured in the laboratory. Now, you have a choice here about what material to use. You could essentially input and write directly the mechanical properties of your material, for example, your tensile strength. Or one thing you could do is you can work with this material database that we pre-compiled, if that can be more useful to you. So essentially, for materials that are typically available in the UK and in Europe, we listed the characteristic properties coming from the Declaration of Performance. You're most welcome, please, to double check those values. I hope I didn't make any mistake. But once you have these values over here, essentially in this part of the spreadsheet, you can select which material you would like to use, and the mechanical properties are listed here are retrieved from the material database. When we look at the tensile capacity, as we saw, essentially there are two potential failure modes. One is the tensile capacity of the bow tie in the narrowest section. So if you have the area of the narrowest section and you multiply by the tensile capacity, you can calculate the tensile force in tension that is necessary to break the bow tie. Something that is a little bit less trivial to calculate is the failure mode that actually you observed in the experiment, which is a mix between compression and shear occurring at the contact interface between the bow tie and the panel. And essentially, this is an iterative process. So you start with guessing a specific force. While you are pulling your panel, the contact surface between the bow tie and your surrounding panel gets smaller because the bow tie is trying to slip out, essentially. And so you have a certain area of contact that depends on how much force you're applying. And if you know the area of contact, then you can decompose your vertical force in some component of the force that goes perpendicular to your bow tie. So you can calculate the stress that goes perpendicular to the bow tie, and you can have a force that runs parallel to the bow tie. So you can calculate your tau, your shear stress. And essentially, there's a formula in the Eurocode 5, which essentially takes the compression force divided by the allowable compression capacity plus the shear stress divided by the allowable shear stress. And when the sum of these two components is equal to 1, then you have a failure. So there might be other failure criteria that you can specify, but I thought that was the most straightforward and among all the available ones. So instead of doing it iteratively, you can take advantage of the goal-seek function in your spreadsheet. So what you want is you try to set the value of this cell equal to 1 while you're changing the value of this cell over here. So essentially you're changing the force in such a way that the failure is equal to 1. And then you can solve it for these properties. And you can see actually now that the solver has finished that you have calculated the second failure mode. And here the final value T is actually the smallest between the two components and is given indication if this is going to be tension or is going to be compression shear failure. One thing that is quite interesting to notice is that is, if you're keeping the geometry fixed, then this is quite sensitive to the material properties. And one interesting thing is that we notice is that actually plywood perform worse than OSB. And the reason is because it appears that failure mode number 2 is actually governing. So please feel free to try different materials and see in your specific case which one is working better. For what I was able to try out, it seems that actually OSB is performing better due to the fact that the shear capacity of OSB is higher than the shear capacity of plywood. The other thing that we need to calculate for the bow tie is the shear capacity when the bow tie is used as a shear connector. So at the bottom of the wall, your bow tie is not just acting as a hold down, but it's acting also as a shear key. So we want to calculate the shear capacity. And to do that, if you know the area in the narrowest section, you can just multiply that by the shear capacity of the material, and you should be able to retrieve this value. So now we can have a look how these properties affect the performance of the wall. Right. Before we dive into the details of the Excel file in which we're going to talk about the how to calculate the capacity of the walls, I just want to briefly mention that there's a document available for you to read, which is linked in the description. And essentially, it contains details about the formulas that are actually implemented in the Excel file. So it provides you really with details about how these quantities are and how the mathematical derivation of the model is carried out, what are the assumptions. And there's also a case study which is benchmarked against some finite element model. So you're most welcome to check it out for more details if you want to know more. Otherwise, we can straightly jump into the Excel file to see how these formulas are actually implemented. Right, here we are. We can talk about the second part of the Excel. So essentially what we are trying to solve is for a given wall that we know the geometry, and for a given loading configuration, for example, a vertical load Q, distributed load, an horizontal force F, and an overturning moment M, we can ask ourselves the question, well, first of all, how much is the wall displacing in the horizontal direction? If we need to double check, for example, the flexibility or the stiffness of our structure. And the second question is, for this given configuration, what is the maximum force going into the bow tie in terms of tensile force, because that will help us in essentially telling us if the bow ties can take that load or not. So how can we do that? So in the initial part of the Excel, there are the materials are specified, and you don't need to do anything over here in the sense of if you choose a particular material when choosing the bow ties, the same material is retrieved. There's a good reason why you want to use the same material for the bow ties and the walls. And that's because if you remember, one of the things that we calculated is the failure at the contact surface between the bow tie and the surrounding panels. So if you use two different materials, you might induce the failure in one or the other. Whereas if you keep it the same, you know that the essentially that the failure that you're estimating for the bow tie in the case, for example, of the failure of the contact surface would be the same failure load for the surrounding panel, because the material and the contact surface will actually be the same. If you calculated the bow tie, also the main properties are retrieved. So you're going to have a tensile capacity, you're going to have a shear capacity, and you're going to have a shear stiffness and a tensile stiffness. Here is where things get a little bit more interesting. You can start playing with the dimension of your walls. So let's quickly jump into the wall database. So what are the key properties when we're going to look at the geometry of walls? Well, our walls is going to be made of number of columns that are connected together. So at this stage, you're allowed to use up to 8 columns. You can probably modify this Excel. It probably won't take you too long to add more columns in case you have a longer wall. But I thought 8 columns was a good starting point. And then the other measurement that you need is essentially the distance between the bow tie and the edge of the wall. That's because when you're thinking about rocking your structure over, the distance between the force of the bow tie and the rocking point is going to give you the overturning moment that the bow tie is resisting to. So it's going to give you the contribution of the bow tie to the overall overturning moment. So this is just some standard dimensions, and they are standard for scalar version 0.2. So when you are in your wall calculator here, you can decide how many columns are forming your wall. And you will see here this geometry is updated. So in this case, we're going to use 6 columns, and you're going to have 18 bow ties per facade. So you have a total number of bow ties, which actually doubles. So it's going to be 36. The other thing you can choose is your height of the wall. We can work, for example, in this case, with 2.4 meters. This number is important because your lateral force also will induce an overturning moment. So depending on that, the amount of force going into the bow tie will be different. And essentially, once you have the geometry set, the 2 parameters here that you see are going to be the one used to repart the force, to break down the overturning moment into the maximum forces going into the bow ties. Again, all these formulas here are hopefully well justified into the PDF that I briefly showed you before, and it's linked here in the description. So please feel free to have a look to if you're interested more into the math behind that. Essentially here, once you know your vertical load, which is going to give you actually recentering effect, is gonna help your wall, and you have an horizontal force and an overturning moment, you can actually, first of all, calculate the shear force going into your bow ties. So in this case, it's going to be 0.8 kilonewton for this particular loading scenario. And you're going to have here a percentage, which is going to tell you how much of the capacity of the bow tie you're currently using. So I believe the capacity of the bow tie was around 3.5 or something. 3.53. So essentially, we are using almost 23% of the capacity in shear. And the same will be for tension. We are using at the moment 2.4, which is around 46% of the available capacity in tension. Now, just bear in mind that these numbers do not have any safety coefficient, and that's on purpose. So the capacity is used using the characteristic values, and the demand is simply a mechanical calculation of how much force is going into the bow tie. When you do your check, you probably want to apply some safety coefficient based on the loading combination that you're using. But hopefully that can be easily implemented once you have the raw numbers. Another reason why the safety coefficient are not provided is that people might use different building codes across the world. So if safety coefficient differ, that it would be better, I think, to have raw numbers to use. The other thing that the Excel gives you back is the lateral displacement of the wall in millimeters. and that is the sum of the 3 different contributions that we talked about in the first part of the video. So the contribution due to the shear flexibility of the bow tie, so it's going to be a translational contribution at the bottom of the wall. We have some shear occurring in the wall. So we have a shear deformation, which is going to create some displacement, and then we're going to have the rocking contribution, which is going to give some other component. And the sum of the 3 will give the final result. And it's interesting how the proportion between these 3 varies depending on the loading condition, but also on the geometry. Very slender walls are more susceptible to rocking, whereas very large and squat walls are more susceptible to shear. So yeah, I really hope this can be useful, and please feel free to add any comment or ask any questions if some of this is not clear. Well, thank you very much for listening. I hope that that was somehow useful to you. Please feel free to add any questions, and please feel free to check out the resources at the bottom of the video. And if there's anything that you would do differently or anything that you would add to the Excel, please feel free to add your comments, because this is a work in progress, so we can always do better. And we are very much looking forward to see more WikiHouse being built, and we really hope this can help the calculation of the structure, especially for maybe some engineers that come across the system for the first time, and they just wonder, how to approach the problem. And so I think that's all. And yeah, thank you very much.